Incidentally, did you know that using nonlinear regression in research is considered out of line? Do you get it? Not in a line, out of line, nonlinear regression. But today we will be confining ourselves to linear regressions and using lines through data points. So let's start with this example where we are examining data of smoking or cigarette consumption and coronary heart disease mortality. All right, so we're going to create a report, and that report's going to include graphs and statistics. We're going to describe the association between smoking and coronary heart disease. We're going to create a linear model. We're going to evaluate the strength and appropriateness of that model, and we're also going to use it to interpret slope and the y-intercept of the line. So first of all, let's take a little look at the initial statistics in the data. I do have the original data on the website if you want to punch those numbers in your calculator. And I ran 2 var stats. So I actually created a column for cigarettes and a column for smoking smoking and coronary heart disease. And I ran them both at the same time using 2 var stats, which is just under 1 var stats. So you have to specify 2 lists, but it's pretty much the same thing. The main 2 things I want to start to look at, when we always look at data, we like to look at our mean and our standard deviation. So just a quick analysis of that. In the 21 countries surveyed, we could write the mean cigarette consumption was approximately. Notice we need to use some weasel words here when we are talking about statistics because we cannot say exactly. That's a very bad word. So it was approximately 2,148 cigarettes per adult per year. Notice the units that we're using with a standard deviation of 808 cigarettes per adult per year. All right. Then the next thing, I just went ahead and did a quick look at the box and whisker plot. Looks kind of normal. Histogram would be even better. And I see that the median value for cigarette consumption was 1,810 cigarettes per adult per year, which tells me, yeah, it's actually skewed a bit, isn't it? Since the median is lower and the average is higher, it looks like it's skewed positively. Okay. So let's go ahead and look at coronary heart disease mortality rates. So my initial statistics, again with the 2 var stats, I have my average, which is 144.9, and my standard deviation, which is 66.5. So I should write this with units when you're doing your test. The mean coronary heart disease rate was 144.9 deaths per 100,000 citizens. Notice the 100,000 citizens, you should make sure you include that in there, with a standard deviation of 66.5 deaths per 100,000 citizens or residents. Okay. And then I also did a quick look at the box and whisker plot, and I'm noticing that this one is also skewed positively because my mean is above my median. So at least it appears to be. I don't have a good histogram, so it's really hard to tell right now. But just based on those 2 values, it looks like it. And that would kind of make sense. All right, so first of all, it's very important to do a scatter plot when starting a linear regression. When you're taking your AP test, you can do the scatter plot and kind of draw it on your test, roughly what it is. They do not expect exactness. So we can see from the scatter plot that we have a positive linear relationship. And so countries with higher cigarette consumption generally have higher rates of coronary heart disease deaths. And there are some unusual features. If you look at the data closely, you can see that Mexico and Greece have lower than expected death rates. Finland has a higher death rate than expected. But they're not like drastic. If I were to tell you, identify Mexico and Greece and Finland on here, I would guess these lower ones would be Mexico and Greece. And I would guess maybe this high one or maybe that high one would be Finland, but it's kind of hard to tell. Since it's really hard to tell which ones are further out, there are no major outliers here. So a linear model is appropriate. The relationship is straight enough. Both variables are quantitative, and there are no outliers. So how are we going to create a linear model? So I'm going to step away from this example for a moment, and let's revisit correlation. All right, so I played with the same applet we've been playing with. I've added something in here where you can see slope and equation of the line. So this is the slope of the blue line and the equation of the blue line. How are we getting this? So first of all, If there's a positive direction in your data, then for an above average value in the x, you would expect an above average value in y. And for a below average value in x, you would expect a below average value in y. And for exactly the average, you would expect exactly the average. By the way, that point corresponds to 0, 0 on this green graph where I'm looking at the standardized data. So it should pass, whatever line we have should pass through the mean point or the average point. For the standardized data, if it's perfectly linear and correlated, that means the slope would be 1, because for every standard deviation that we would go in x, I would go 1 standard deviation in y. Okay. And if it was negatively correlated, I would expect it to be -1. So notice the slope of this line right here. So you can see this equation right there, right? And my correlation is 0.99. What's the slope of this line? 0.99. That makes sense. We were kind of saying that if it's perfectly correlated, it should match exactly. The less correlated it becomes as I move points around, the slope diminishes and it gets closer to 0 until I start to get a pattern that's starting. Now we're going from, we no longer have a strong correlation, we have a moderate. And then I can even do this and make it all the way to a weak correlation. Okay. So we can play with these points, and you can see one thing that's going on. This blue line right here, if you look at that slope, what this has to do with is the behavior should be the same. If point E is about 1 standard deviation above the x average value, right? So you can see it right there. Well, do we expect it to be 1 standard deviation above the y value? You can see, no, it's closer to 3/4 above. And so what we do is if I take these original standard deviations and use it as a slope, that works as a slope for my blue line. So for point E, like I said, it's 1 standard deviation above the average. So I would expect the y value to be 0.95 standard deviations above the average. All right, let me go ahead and move a point so I can kind of get it further out here. I'm going to kind of lower it so you can't see. I don't want it to be, that's the problem with linear. My correlation's too high. That's a problem with outliers. All right, so I don't really want, okay, so I'm moving my points around. Okay, let me lower my correlation a little bit more. Okay, so now we have a correlation of 0.47, so about a half. So now you can see when I do this, if I have, since it's not correlated, now these aren't matching so well. But basically, let's look at this point out here. If I'm 2 standard deviations above the mean, so I'm like right here, okay, then I only expect to be 1 standard deviation above the mean in the y direction. So I can go backwards, put in the actual standard deviations, and figure out the slope of my original line. Okay, so basically what we're saying is that the number of standard deviations is related to the correlation times the number of standard deviations for the x. So there's a very strong relationship there. When we have this slope, it's pretty much the correlation coefficient. So again, moving 1 standard deviation from the mean in x moves our estimate, r standard deviations from the mean in y. So what does that mean? Well, if I want to determine this equation for the line of regression, all I have to do is figure out r, figure out the standard deviations for x and y, and then that'll give me the new slope. Then I can use the point slope formula, and what is this point in here? Well, if you look, it's kind of mixed in. That's this point over here, the mean point. So if I know the means of the data, I can go back and actually calculate the regression line. Okay, so we're going to go ahead and do that. But before I do that, let me go over some basics of the linear model. First of all, when we're writing it, the predicted value, this is called y hat, so it's got a y and a hat, is the estimate made from the model. The true value is y. The mean of y should be associated with the mean of x, so the line should go through the mean point, x bar, y bar. Now when you do the inverse, say you want to go backwards, don't just flip the slope. That's tempting, but it doesn't work because r is the same both ways when you switch x and y. So we'd actually have to do a separate calculation for slope there. Also remember, r is not the slope of the regression line. It is the slope of the line that goes through the standardized points, where we're talking about the number of standard deviations. R does not predict what percent of points the line will pass through. Okay, so it's just a relationship between standard deviations of y to standard deviations of x, or vice versa. So let's go ahead and calculate the slope for the linear regression for the smoking. And this is the formula we want to use. The slope is r times the standard deviation of y over the standard deviation of x. Well, where do I have that data? Here's the r I had before when I calculated the linear regression and correlation coefficient. And I can get my mean from the right here. I have my x bar, right? And so I have 66.5. Whoops. Let me go put that data there. That'll help. All right. So I need the 66.58 for the y goes on top here. And the 808, which is roughly here, goes on bottom. So I need these two standard deviations. I multiply them by that r, and I get 0.60. I also need the mean point. So the x-coordinate is 2148, and the y-coordinate is 144.9. Use the point slope formula, and I have y hat minus 144.9. Notice the hat equals, there's the slope, 0.060, x minus the x bar. Then I'm going to actually replace this with more meaningful variables, and it's really recommended you write your equations this way. So I'm going to say coronary heart disease death rates minus 144.9 is equal to, and I distributed this here, multiplied it out, 0.60 times cigarette consumption minus 128.9. Okay. Then continue with the math, adding 144.9 to both sides, I get plus 16. So this was sort of a hand calculation of the linear regression. And when I actually run the linear regression on the calculator, you can see it's very close. There is A, which is the slope, 0.60. And there's my y-intercept, 15.6, which is very close to 16. Okay, so how do we interpret the regression? So for every 1 standard deviation increase in smoking consumption, we expect 0.73 standard deviation increases in CHD death rates. Now, normally you're not going to write that part because most people don't want to talk about standard deviations. They want to talk about coronary heart disease death rates versus smoking, not really the standard deviations of the both. So they want to see the more direct relationship. So we rewrite our equation, and there it is. Make sure you have the variables so it's in context. And here's a great sentence you could use to describe it. The model predicts, notice predict, that a country in which there is no cigarette consumption, the CHD death rate would be 15.6 deaths per 100,000. Notice the units. And here we're talking about this y-intercept here. So we are interpreting that right now. Okay. Furthermore, according to the model, for each additional 100 cigarettes consumed per adult per year, so there's an expected increase of 6 deaths due to CHD. Okay. Notice how it says according to the model. An expected increase, not that it would for sure increase. So you've got to put in what we'll call the weasel words, where you're not saying for sure this will happen. This is what is expected. This is what is predicted. Okay, so that is how we can interpret this. Now, the extra thing I want to do is go ahead and look at the inverse, just so you understand what you can do. So there's a temptation to solve for that regression we just did. Don't. Because r is the same both ways for the variables. So you can't just flip it. Calculating the slope, let's go ahead and do it. We're going to use the same formula. Now, instead of having the 808 on bottom, I'm having the 66.5 on bottom. Again, that's the only part that gets flipped. The R is the same. And you can see I got a slope of 8.87. Then I calculate the equation using the mean point, and I got to switch those too, right? So I'm going to say, and it's here, it's good to avoid the X and the Y because that's why it's nice to have the cigarettes and CHD, because then it's less confusing, I hope. So we have cigarettes minus the y-intercept, not minus the y mean, minus the mean cigarettes really, equals the slope times coronary heart disease minus the average death rate for coronary heart disease. Distribute the 8.87, add 2148 to both sides, and this is the equation you get. Now you can very quickly, I am not expecting you to be calculating a lot of linear regressions by hand. You can very quickly calculate the linear regression on your calculator and see that that matches what we got. Remember, you've got to switch your X list and your Y list if you are switching to the inverse. So to practice these concepts, there are two great problems at the back of this chapter, problem 27, and then just do parts A through D of problem 33 on pages 191 to 192.